Okay, good afternoon and welcome back. We will continue the discussion of yesterday where we discussed the relic abundance of cold relics, and we will do it in a way that is more quantitative today. Yesterday was just a sketch, was just an estimate. Today we will do an actual calculation that if you want to do it properly, it has to be done numerically, and I will show you what equation you have to solve, but we will also solve this differential equation semi-analytically. Okay, so let me do a brief recap of what we saw yesterday. Okay, so we assume the existence of some new particle chi, and for this discussion, let's say it's not a real particle, so the anti-particle of this particle is different than the particle itself. That's why I write chi bar, okay? If it's a Dirac fermion, this is the case. If it's a Majorana fermion, it's very similar to the discussion, just keeping track of the factor of 2. Let's focus on one case for concreteness, okay? So what we learned yesterday is that if this annihilation process has a rate large enough to keep these dark matter particles in thermal equilibrium with, I call now B1 and B2, so I will introduce the symbol Bi to denote generic bath particles belonging to the thermal bath. This could be electrons, muons, W, Z, anything belonging to the standard model, or even some degree of freedom beyond the standard model that is in thermal equilibrium with the standard model. Okay. So if this reaction is efficient, if this particle get to thermal equilibrium, they eventually decoupled. We focused on the regime of the so-called cold relics, so decoupling temperature smaller than the mass, and we found this equation here. Okay, so plus small corrections. And I remind you that XF is defined as the mass over the temperature. So it's a way to define the decoupling temperature in a way that is dimensionless. And so I use the mass to make the temperature dimensionless. I take the inverse for reasons that hopefully will be clear today. So this XF was found to be around 25 for typical numbers of WIMPs. So mass hundreds of GeV, cross-section around the picobarn scale, and then Planck, of course, we know it very well, okay? And finally, if we know XF, we can compute the abundance of this particle today by using the omega variables that I introduced yesterday morning. And this quantity was found to be approximately 0.1. Okay, so if you normalize the decoupling temperature to be around 25 in this X variable, and the cross-section to be around 1 picobar, then you are in the right ballpark, okay? So the characteristic dependence is with the inverse of the cross-section, okay? It depends, and that we'll discuss in a second. Let me just remind you that it's not the cross-section, it's sigma times V, the combination that matters here, because we are computing an interaction rate. And so the interaction rate needs to know about the number of targets, the cross-section, but also the relative velocity, okay, between the two particles that collide. And there is this bracket symbol here, which denotes a thermal average. So I take an average over all the possible incoming states for this annihilation, okay? Okay, so the best way to introduce the topic of today is through a plot. Okay, so let's try to make a plot where we plot y chi. So y chi, remember, is n chi over s. It's what we called yesterday the comoving number density. So a good way is to plot y chi as a function of x. What is x? Is m chi over t. Okay? So remember, we are in the radiation-dominated universe. There is a relation between temperature and time. So for each time, there is an associated value of the temperature. And for each temperature, there is a value of x. Why it's convenient to choose mx over t and not the opposite? Well, as the time goes on, the temperature decreases. And so as the time goes on, the variable x grows. Okay? So if I look at this horizontal axis from left to right, I'm going forward in time, which is usually something good if you want to visualize the evolution. Okay? So in this plot, I drew a dashed line, and this dashed line is the equilibrium. Okay? This dashed line is the equilibrium distribution. Why is the equilibrium distribution? Remember that y chi equilibrium is n chi equilibrium over s. Okay? So roughly speaking, you can divide this expression into relativistic regime and non-relativistic regime. Then you can do the calculation exactly, okay? But just to understand the transition. In the relativistic regime, you have t cube over t cube for x much less than 1, okay? So if x is much less than 1, you have a temperature much larger than the mass. So you are in the relativistic regime. In the relativistic regime, the number density grows like t cube. The entropy density is always t cube. In the non-relativistic regime, you have the Maxwell-Boltzmann distribution over t cube. So you can get the precise expression with all the numerical factors, but the interesting thing here is that you are going to drop this variable exponentially, okay? And so this is precisely the line I drew here. You have, for x much less than 1, a constant value, okay? And then for x going to, in the non-relativistic regime, you have this exponential suppression, okay? Now, this is the equilibrium, and we know that if I identify xf here, we know that for x less than xf, before the decoupling, before the freeze out took place, I know that the dark matter particles were in equilibrium, okay? So I can put a solid line in this plot, which I call the solution, y chi, the actual evolution of chi particles. And for x below xf, I must have been in equilibrium, okay? Then our brutal approximation that we made yesterday was the one of instantaneous decoupling. What does it mean? For x below xf, so temperatures larger than Tf, I'm in equilibrium. After, this y variable is constant. Okay? So if I plot the solution that I gave you with equations yesterday, this is what we did yesterday. Okay? If you look at this plot, this is the result of our approximation of instantaneous decoupling. Of course, we do not expect this to be true, okay? In particular, you find a solution which is continuous at decoupling, but the first derivative is not continuous. You see there is a kink here. And so this is just the result of an approximation. If you are able to track, and this is the goal of today, how to track this variable properly, then you see that this function here is smooth around this point. So the goal of today's lecture is to develop the mathematical tool to understand what's going on here, okay? We want to understand what's going on here, and the reason is that the instantaneous decoupling cannot tell us more than what I just drew, okay? Of course, the mathematical tool we are going to build will allow us to track the distribution everywhere, not just here, but here and here, the evolution is straightforward, okay? All we have to understand is what happens shortly before and shortly after the decoupling time, okay? And I can give you a preview, okay? So this is the solution, and I call this ID, instantaneous decoupling, okay? So this is the solution you find if you assume instantaneous decoupling. What happens if you do the full job? I will derive that, but let me give you a preview based just on physical considerations. So imagine that you identify the decoupling temperature. So when the distribution stops being the thermal equilibrium one, then of course in the universe there are still chi particles that can occasionally find each other, okay? So you can still have these annihilation, they are called post-freeze-out annihilations. Why? Because they come post-freeze-out. The distribution is not the equilibrium one anymore, but they occasionally happen, and this is a channel to suppress a little bit more the contribution of these chi particles to the energy density of the universe. So if you do, as we will, if we do the full solution, and let's see, I see chalks of other colors, but they are very, very small, but okay. Maybe I can do this. No, I cannot. Bad idea. Let's try this. Okay. So the numerical solution, the full solution, will be this blue line, okay? So you see, it will become smooth here, and there will be this post-annihilation taken into account. You will be away from equilibrium. We are after freeze-out, so we are away from the equilibrium. But still, chi and chi bar find each other and annihilate, and eventually you really get to a constant. And as we will see, this correction suppresses a little bit the density, and so with the instantaneous decoupling, you tend to overestimate the abundance. But no, you don't go too much far away, okay? So it works quite well, the instantaneous decoupling approximation, but if you want to do, and you should do a better job, because the dark matter abundance is measured with very, very high precision. If you want to match the experimental accuracy, then you have to do a better job, okay? So that's what we're going to do today. We're going to develop the mathematical tool that allows us to keep track of the distribution here. Eventually, we will write the Boltzmann equation. It doesn't have an analytical solution, but you know, we will try, if there is time, to sketch a semi-analytical solution, and if there is not time, I can just give you the equation and tell you how to solve it numerically. Okay? So this is the plan. Okay, so the subject is Boltzmann equation, which is something I was saying yesterday that it doesn't appear for the first time when you study physics in cosmology. Okay, it's something that, of course, belongs to a wider range of systems. But now we will develop the version of the Boltzmann equation that applies to an expanding universe, and it had to be different. Okay, so how it will be different? I write this in a very generic and general form as an equality between the action of two operators on the distribution function, okay? So my goal is to find the distribution function of dark matter, f chi of the energy and the time. Let's remember, energy, because I have the cosmological principle, it doesn't depend on the location, it cannot depend on where I evaluate that, and also it doesn't depend on the direction of the momentum, just on the side of the momentum. So size of the momentum and energy, I have the dispersion relation, they're the same. I use the energy, okay? And then the time, of course, because the universe evolves. And so these L and C are operators in the sense that they act on a function, okay? And they have names. L is known as the Liouville operator. And the Liouville operator accounts for the geometry. What does it mean? It means that even if there are no collisions, if the dark matter particles do not destroy each other, there is no process creating dark matter particles, there is nothing happening, the distribution has to evolve because of the geometry of the expanding universe, okay? So the universe is getting bigger, the distributions change because it's changing the space-time, okay? So this effect has to be taken into account, okay? On the left-hand side, we have the collision operator, and I call this dynamics. So by geometry, I mean the geometry of the expanding universe. By dynamics, I mean microscopic processes that change the number of particles of dark matter, and so they affect the resulting distribution, okay? So we will discuss the two of them separately, and in particular, we will see that this equation, if you write it in the most general form, even if you assume the cosmological principle and all the assumptions we made, it's an integral differential equation. So integral differential equations are particularly expensive to solve computationally, and we will ask ourselves, when is it possible to reduce this integral differential equation such that I get an ordinary differential equation? And I will identify two cases when this happens, and these two cases are precisely freeze out and freeze in. Okay, so we will discuss freeze out today and freeze in tomorrow. Okay? Okay, so let's start from the Liouville operator. So the Liouville operator, because that's a Boltzmann equation. If you want, this equation defines the two operators. So you have on the left-hand side the derivatives of the, I will write now an expression, and then the right-hand side is telling us why the distribution function is changing. So you... Exactly. But then if there is a process where W plus W minus find each other and they create chi bar, that's an addition to the distribution function. You change the distribution function because you produce dark matter particles. Okay? So I mean, if you are familiar with the Boltzmann equation, not in the expanding universe, the concept is the same. On the left-hand side, you have the variation of distribution, and on the right-hand side, you have the reasons that make the distribution change. No, the expansion of the universe is described by the Liouville. So in particular, if there is no expansion, I will discuss this. If there is no expansion, the Liouville operator is equal to 0. Okay, so I'm just, I mean, in the end, there must be a balance between how the F changes and what feeds the change in the F, okay? Okay, so the Liouville operator, the derivation of the Liouville operator is a bit technical, okay? And it's a beautiful derivation. I promise some notes that will not be ready by the end of this week, by the way, but they will hopefully in few weeks. But I will tell you what to do if you want the notes tomorrow at the very end of the lecture. Somebody asked in the break. Don't worry, I will tell you. It's quite technical, but the procedure is very nice. Like you start from something that you know in flat space, you write it in a covariant form, and then once it's written in a covariant form, it's valid in any coordinate system. It's the way you do several things in general relativity, okay? So I will not do the derivation here because it will take too much time. I will give you the expression, but then we will convince ourselves very quickly that makes a lot of sense, precisely for what we've been discussing now about the meaning of the Liouville operator. So let me give you the definition of the Liouville operator. The Liouville operator has this form. Okay? So you see, if the expansion of the universe is not there, Hubble is 0. The Liouville operator is telling me that in the absence of the expansion of the universe, in the absence of any macroscopic process creating the particle, the distribution function doesn't depend on time. That makes sense. So we want to understand how this correction makes sense. Okay? So to understand how this correction makes sense, we can do the following. We can take the phase space integral. So this is the definition, okay? And again, it's a very nice derivation, but I give you the result. Now, let's see if this result I gave you makes sense. So if I take this integral, so I take the integral of L over E, okay? L over E is, and I take the integral over the phase space, and I multiply by g chi. G chi is the number of internal degrees of freedom of the chi particle, okay? In such a way that the first term, you know, I have the integral of the time derivative. I can, since this is a partial derivative, I can bring in outside of the integral, and so I have the number density of chi derived with respect to the time, okay? And then I have an additional piece, which I will write. Okay, so I have L over E, so I have H P square over E df dE, okay? I just took the expression here and I computed this integral. The first one is quite easy. I have the integral of the time derivative, so I get the number density. Remember, the number density is this integral over the distribution function. The less obvious term is this one. It depends on Hubble, okay? We want to understand if this term makes sense. Let me do a couple of approximations, okay? Sorry, no, not approximation, a couple of steps without writing a new equation. First of all, I take Hubble and I bring Hubble outside of the integral, because Hubble is describing the cosmological background, so it doesn't depend on the momentum. So I can take Hubble and I bring Hubble here, okay? Then I do df dp, dp dE. I know that, so remember, in this form I had df dE, but E and P are related through the dispersion relation. Okay? So I can express f as a function of P and take the derivative of f with respect to P. I have to remember the factor that tells me how I compute the variable, the derivative of a function, okay? And this dPdE is what? It's E over P. Why? Well, I can read this here, okay? The differential of this equation, the mass is constant, okay? So E dE is equal to P dP. So if I take the derivative here, I get E over P, okay? So it's just a change of variable. But now this E simplifies this, and this P simplifies this. So I end up with a quite simple integral, which I can compute. Let's compute it here. So I have an integral over d3p, but I can integrate that in polar coordinates. Remember that the distribution function depends only on the absolute value of p. So I can go to polar coordinates. So the integral there up to the factor Hubble, that I can take it out for a moment, I'm talking about g chi integral of 1 over 2 pi cube. I go to polar coordinates. Okay? This is d3p in polar coordinates. Then I have an additional power of p, so let me put a p cube here. Okay? And then I have df dp. Okay? So what do I do with this integral? I integrate this by parts. Okay? If I integrate this by parts, well, let's see, I have 3, okay, minus 3 g chi 4 pi p square over 2 pi cube dp f chi. And then let's not forget that when I integrate something by parts, I have boundary terms. But now the boundary term, if you look at here, is p cube times f. If I evaluate this at the origin, p cube gives me 0. If I evaluate f for infinite momentum, I also expect that to be 0. I am assuming that the distribution, the product p cube times f at infinity goes to 0, but that's a reasonable assumption. So the boundary term can be neglected. And in the end, this is what? This is the number density. Because it's 4 pi p squared dp. This is d3p times f. It's by definition the number density. So I end up minus 3 n chi. Okay? That's the result of this integral. I go back there and I realize that if I take the Liouville operator integrated so this is what I was computing on the other blackboard, I get dn chi dt plus 3h n chi. So plus because I have a minus here, but I had a minus here. So minus minus gives me a plus, and then I should not forget about the Hubble factor. Okay? So the integration over phase space of the left-hand side of the Boltzmann equation gave me something interesting. It gave me the time derivative of the number density plus 3h n chi. Okay? So I want to discuss now with you if this makes sense. Okay? So imagine there are no collisions. What does it mean? There are no processes creating or destroying dark matter particles in the early universe. So in other words, C is equal to 0. Okay? I will give you in a second an explicit expression for C. But let's focus on the case where collisions are absent. So let's focus still on the left-hand side. So if C is 0, I get dn chi plus 3n chi equal to 0. So if there are no collisions, I found this result. Does it make sense? Why? Mm-hmm. Yeah, so in other words, if I switch off all the collisions, I should expect that this is non-zero. The number density changes with time, but only because the universe is expanding, not because there are processes creating or destroying dark matter particles. So it makes sense to have an additional piece. Now, this 3 is precisely connected to the number of spatial dimensions. So it's a volume factor. And we can check this explicitly, because if we compute this is the quantity that stays constant if I switch off the collisions. Okay, so if the collisions are switched off, n chi times the scale factor cube is constant, because the universe is getting bigger, but this is precisely how much. So if I compute this derivative, I get, I do the usual Leibniz rule. I collect a common factor, and this is what I find, okay? So you see that if this is equal to 0, then this time derivative is equal to 0, which means n chi a cube is constant. So that's precisely what we were expecting. And you see this factor of 3 comes from the derivative of this 3 here. So that's why I call it a volume factor. Imagine we had 5 spatial dimensions. If we had 5 spatial dimensions, we would have had a to the 5th here. So there would have been a 5 here. Okay, but we know that the spatial coordinates are 3, and so that's what we found. So even though I did not give you a derivation for the Liouville operator, let's say that what we found is actually reasonable, okay? Because from the expression I gave you, if I take the integral over the phase space and I switch off the collisions, I find what I expect to find, okay? And in particular, the term due to the expansion, which is this one, does exactly what I want, okay? Okay, now let's switch to the collision operator, which is the left-hand side, the right-hand side of the Boltzmann equation. Okay, so to save some space, let me, because now I want to start, you will see the equations will get long quickly, so it's good to use the space wisely. Let's see what we can do. So anyway, I hope that it makes more sense now, the equality. So I define the Liouville operator as something that is vanishing if there are no collisions. No, there is the expansion there, yeah. So if you want, the Liouville operator is the generalization to a more beyond Minkowski spacetime of the usual one that we are very familiar with outside of cosmology. Okay, and then I also can delete this, because now we understood the Liouville operator. The Liouville operator is the easy part, because we know the metric. Once we know the metric, we know everything. The non-easy part is to account for the dynamics, and we will do that. Okay, so maybe I can keep this blackboard here, and then I can do the following. I can emphasize this equation, and then we don't care anymore about the explicit expression of the Liouville operator for today. What we care about is this result. If I take the phase space integral of the Liouville operator over f chi, then over E, sorry, Liouville operator applied to f chi over E, then I get this. Okay, so this doesn't look so bad now because this equation is integro differential. There are both derivatives and integrals acting on the phase space distribution, so it's very difficult to solve. You can do it, it's just more expensive computationally. But you see that if you take it's just the phase space integral of the left-hand side, then you get something that is not so bad. It looks like what could be the left-hand side of a differential equation, ordinary differential equation, and not integral differential anymore, where the unknown function is the number density, okay? So our goal will be to write down a differential equation for the number density, because solving for the phase space distribution is something that if we can avoid, we would like to avoid. You cannot always avoid that, as we'll mention tomorrow. But our goal should be to write down an ordinary differential equation for n chi. We will see that it's possible, starting from this, to get this, and then to fill this with only n chi without any residual momentum dependence. But it's true under some assumptions. So we have to state these assumptions very clearly, okay? But for the case of interest of today, these assumptions are well justified. Okay, so let's see. We have 3 blackboards. Hopefully, they will be enough. Our focus now is on the collision operator, which I call C. Okay? So what I call the collision operator is actually the sum of many contributions, because there is, in principle, more than one process that changes the number of dark matter particles, okay? So for each one of them, we have to write the resulting collision operator and then sum overall on them, okay? So to simplify the discussion, we will assume that there is one process that is the dominant contribution of dark matter depletion or creation. If we have more, we just repeat what I'm about to do over and over, okay? So let's assume that the main production or destruction process is B1, B2, chi bar. It could go either way, okay? So it could be a process where B1 and B2 meet each other and produce dark matter, or it could be a process where chi and chi bar find each other and they annihilate away. Now, since I'm working in momentum space, I left some space here to I have to specify the momentum of each one of these particles, okay? So I call K1, K2 the momenta of the bath particles, and P1 and P2 the momenta of the dark matter, Okay, yes. Oh, well, you can put a partial, but the number density depends only on time. So partial and total are the same, but you're absolutely right. Strictly speaking, would be a partial. But then since that's the only variable, because the number density depends only on the temperature or time. So it's common to denote that as a total. But if you follow the derivation, you are correct. Other questions? Okay. So I put the momentum. These are 4 momenta. Is the mic working? Yeah. These are 4 momenta, and they're 4 momenta because we have to use a relativistic description. There will appear matrix elements in this collision operator that I'm about to write. And so it's common to use these matrix elements with the relativistic normalization of states and so on. So these are 4 vectors, okay? Now, for this process here, the collision operator can again be derived from first principles, and I will give you the derivation in the notes. But let's try to construct it together by looking at the variables and the quantities that we expect to appear, okay? So this collision operator, so there is a factor of a half. To understand this factor of a half, you have to do the derivation, but it's a consequence of the, again, the relativistic normalization of states. If you remember how you define the normalization of states in a Lorentz invariant way, there are these factors of 2 that are perhaps familiar. Then there is a phase space integral over all the momenta. So let me write so I will stop here for a second to explain what I'm doing. So there is what? Oh, here, yes, cube, thanks. So this is the Lorentz invariant phase space, okay? D3k divided by 2 pi cube 2 E1. This is Lorentz invariant. This factor of E1 makes it Lorentz invariant. So I'm calling K1 the momentum of this, and I'm calling E1 the energy of the momentum K1, and they are connected through the usual dispersion relation. There are this factor of G1 and G2 because it makes sense that the rate for this process is proportional to the internal degrees of freedom of these particles. The more degrees of freedom, the more frequent will be the collisions. Then there is another integral over P2. P2 is the momentum of chi bar. And I stop here with the integrals. Why? I'm not integrating of this because the function is the function of chi. So this function of chi depends on P1. I cannot integrate over P1, okay? So that's the amount of phase space integrals. Then I have 2 pi to the 4th delta 4. You know, this is the energy momentum conservation. So K1 plus K2 must be equal to P1 and P2. Otherwise, what I'm doing doesn't make any sense if I don't conserve energy and momentum. And here, there is the interesting part. So here I have the matrix element for the direct process. Okay. Then I have F1, F2. So let me stop 1 second before I put the rest. So in the first line, I put 3 integrals. Why? Because if I want to describe how these chi particles are produced, I have to sum over all the possible incoming and outgoing directions of the other momenta, okay? So I have to account for all the possible combinations. Here, P1 is fixed, because P1 is the argument of this function. But then all the others, I have to sum over all the possible combinations under the constraints of energy momentum conservation, okay? So this first line is telling me sum over all the possible contributions, make sure that you don't violate energy momentum conservation, and then multiply this by what? Well, with a plus sign, there must be a contribution from the direct process, the production process, when I read this reaction from left to right. So that's why I put the matrix element from left to right, okay? And then this must be proportional to F1 and F2. So the probability, and of course F1 and F2 will be functions of K1 and K2, and they will be equilibrium, F1 and F2, because particles B1 and B2 are in thermal equilibrium. And then for the final states, I have this 1 plus or minus F chi. These are the so-called poly-blocking or Bose enhancement for fermions and bosons. Okay? These are just statistical corrections that we are going to avoid in a second, but just for completeness. Then you have an identical term, but with a relative minus sign. Why? Because if you read the reaction from right to left, you are destroying chi particles, and so it must be a negative contribution to the variation of the F. Okay? And so here you have F chi bar, and then you have analogous factors for this. Okay, so this is the most general collision operator for that specific process. Okay, so you see it's quite long. You can imagine what happens if you start to have more of this, if you start to have a higher multiplicity of states, but this is what you have to do, okay? So far there are no approximations, okay? So now we ask ourselves, can we simplify? And the answer is yes. And how do we simplify this? There are several things that we can do that are, technically speaking, approximations, but they're very, very justified. The first one is neglect quantum degeneracy effects, which is just telling you that 1 plus F is 1. Okay, so in the early universe, the occupation number, you're quite far away from degeneracy. F is always 1. You can check with the typical numbers. So all of these corrections are actually not so relevant, and they simplify. I mean, removing them simplifies our life a lot. So we will do that. Then the other assumption is CP conservation of what? Of the interaction mediating that annihilation process. So if you conserve CP, then you have this. You have an equality between the square matrix element for the inverse and the direct process, so I call it just M, okay? And let me also say that there are different conventions, okay? The one I use, the one I like, is to take these square matrix elements average over initial and final states. This is not what you do when you compute cross-section, the textbook level. You average over the initial and sum over the final. But here, you average over both, just because initial and final states are not, you are considering both processes, okay? So it's good if you average over all of them, and then this G take care of this averaging procedure. The counting works, okay? So just technical information, these square matrix elements are average over all the states, initial and final. And finally, the third approximation I can make is that there is no asymmetry for dark matter. So in other words, the number density, the phase space distribution for chi and chi bar is the same. Okay? This is different from the assumption 2, okay? Because maybe there was something at earlier times that generated an asymmetry, and this process still respects CP, okay? So I'm assuming two separate things here. One is about the interaction generating that variation of chi particles. The other one is about, if you want, initial conditions. There was no chemical potential injected in the dark sector. And of course, this assumption, if you are dealing with asymmetric dark matter, this is a very bad idea to assume, because you destroy the starting assumption, okay? So in the freeze-out case we sketched yesterday, we assumed that there was no difference between the phase space distribution of chi and chi bar, and so they are equally abundant. If that is the theory of dark matter, today we would have an equal amount of chi and chi bar with the same phase space distribution and the same number density, okay? So let's see the implication of this assumption. So the collision term, now I don't put an equal, but it's almost an equal, so it's a very good approximation, is 1/2 G1 so I will not write all the momenta, and I don't need to specify what the first line has become, just because it's the same. So the first line doesn't change. What is going to change is the second line. And the second line, now I can collect a common factor, m squared, okay, because of this assumption. I can neglect the 1 or plus or minus. And so it gets very, very simple. It becomes F1, F2, equilibrium, okay, multiplied by 1 minus f chi squared, okay, because f chi and f chi bar are the same, divided by f1 equilibrium, f2 equilibrium, okay? So you see how simple this became, okay? There is something else I can do. The something else I can do is a consequence. It doesn't require any new assumption, but if I neglect quantum degeneracy effect, so if 1 plus f is actually 1, it means that I'm describing all the particles, bosons and fermions, with a Maxwell-Boltzmann statistic. The Maxwell-Boltzmann statistic is the expression you get once you remove the plus or minus y and 1 in the quantum distributions, okay? So F1 equilibrium, F2 equilibrium is just the product of these two exponentials, okay? Because the Maxwell-Boltzmann distribution is e to the minus e over t, okay? Now you can combine these two. You get E1 plus E2 in the numerator. What is E1 plus E2? Conservation of energy is E chi plus E chi bar. Okay? E1 plus E2, E chi bar. The energy is conserved in the process. And so I just proved here that the product F1, F2 evaluated at the equilibrium is equal to F chi bar, both evaluated at the equilibrium, but this is also f chi squared, okay? This is just a consequence of two assumptions I've already made. One, which is not really an assumption, it's conservation of energy. So it's not, I would not call it an assumption. The other one is neglecting quantum effects, okay? So let me do something here. So I can take this identity here now, and I can replace this in this expression. Okay, so this is what we found. Okay, now this is our expression for the collision operator in the assumptions we made. Let's try to go back to the Boltzmann equation. Okay, so from now on, the collision operator will be this one. Okay, you see there is the Liouville here, there is the Liouville integrated, there is the collision. Let's see what we can learn once we assume this form for the collision operator. So the full expression is this, but under very reasonable assumptions, we simplify that. Okay. Okay. So what I will do now is to take the integral of both sides of the Boltzmann equation now, okay? So I will take the integral of Liouville over the energy and then collision over the energy, okay? And once I do that, I get dn chi dt plus 3h and chi equal to what? To a lot of integrals that now I will write it only once. I will write all of them so we visualize them. This is P1 and this is P2. Okay, so now notice how this factor of 2 combined with the fact that I am integrating not the collision operator, I'm integrating C over E because I'm doing L over E here. So I get an additional factor 2e, which combined to the integral I'm doing gives me also the Lorentz invariant phase space for the chi particle. So everything looks nice. Then I have 2 pi to the 4th d4 p initial minus p final, and then I have the remaining part with the distribution. Okay, so this is an important point where I wanted to get. And now we can discuss what we do with this. Okay, so this is the... Oh, yes, yeah, otherwise, thank you. So there is also an m squared, of course. Thank you. Okay, so this is the full Boltzmann equation, okay? So on the left-hand side, we have what it looks like, what it would be an ordinary differential equation, n, okay? Here, unfortunately, we still have f chi, okay? This f chi depends on the momentum, okay? And so to be precise, I was a bit sloppy here. Let me be more precise. This is f chi of P1, f chi of P2. Okay? So there is a momentum dependence in this distribution. I was a bit sloppy, sorry. I have to be more precise here. These f depend on the momentum, and the same is true for the equilibrium one. Okay? But the problem is that if I want a differential equation for n, and I still have an f which is integrated over, I cannot make too many progress, okay? So the question is, when integral differential becomes ordinary. So ODE, the differential equation that we are familiar with. And so something must happen here, okay? Something must happen to this term, okay? And what is actually happening here? We have two options, okay? The first one, which is the one that will eventually define the freeze out, is the following, is chemical equilibrium lost, kinetic equilibrium preserved. Okay? What do I mean? Chemical equilibrium is the equilibrium of the reactions that change the number of particles. So chemical equilibrium is the equilibrium of reactions like this. Okay? You are in chemical equilibrium when this happens often enough. Okay? But you can still lose chemical equilibrium while preserving kinetic equilibrium. Kinetic equilibrium is describing elastic scatterings. So you are not changing the number of chi anymore, but you are redistributing the momentum. Okay? So you freeze the chemical potential of chi, you freeze the number of chi in a comoving volume, but you make them thermal. Okay? So if you are in this situation, and for the freeze out we discuss, we are in this situation. Why? Because this process goes out of equilibrium as a consequence of a Maxwell-Boltzmann exponential suppression of chi bar. But this process here is still in equilibrium because B1 is a bath degrees of freedom with the full temperature cube abundance. And so the number of targets does not suffer this exponential suppression. So it's very reasonable. You can check that it works, but also without putting the numbers, it's reasonable that this process, when this process goes out of equilibrium, this one is still in equilibrium. Because for chi, it's very hard to find chi bar to annihilate with, but it's very easy to find a B1. This is exponential suppressed, this is not. Okay? And so if this is the case, then f chi over f chi equilibrium is equal to n chi over n chi equilibrium. This is the condition of kinetic equilibrium, which means that up to a constant, f chi is equal to the equilibrium one. Okay? If you want, it's a Maxwell-Boltzmann distribution with the chemical potential. That's what you want. Of course, it also makes sense because if you take the integral, if you bring f chi on this side and you take the integral of both sides, then you find an identity, which is something we want. Okay. So this is interesting. Why? Because this is something that depends on P and on the time, but number densities depend only on time. So if I make the assumption supported by the argument I gave you, and you can check with numbers, but if I make the assumption of kinetic equilibrium, then this ratio, this very annoying ratio that is appearing inside my phase space integral, it's something that doesn't depend on the momentum anymore, and you can take it out of the integral. If you take it out of the integral, then the integral is easy, and it can be computed. Okay? So this is freeze out. The second situation where you are allowed to take the full Boltzmann equation and make it become ordinary is freeze-in. Freeze-in, it's even easier. It corresponds to F chi much less than F chi equilibrium. So freeze-in candidates, we will discuss them tomorrow, are candidates that are so weakly coupled that they never get even close to being in thermal equilibrium, okay? And so if they never get to thermal equilibrium, their distribution is much smaller than the equilibrium distribution. So 1 minus a small number can be approximated to 1. And also in that case, of course, it's even easier because the additional contribution in the square bracket, the one that is bothering us, becomes 1, okay? And so it's super easy to be computed, okay? So these are the two cases where you can start from that expression above and the right-hand side becomes something manageable, okay? And so for the remaining 20-25 minutes, let's discuss today case 1, which is what is known as freeze-in. Freeze-out, sorry, freeze-out. Which is the case we discussed yesterday in a qualitative way, but now we have a differential equation. We have a differential equation to keep track of n chi. N chi and y chi are related, so we will eventually write down an equation for y chi, but we have a tool now. We have a differential equation to describe the time evolution of this quantity. So that's what we will do, okay? Sorry? No, because you have to, you have to, it's not a freeze out you solve with the usual momentum, with the usual n-chi differential equation. There are situations, of course, in the simplest dark matter models of freeze out, this is true. You are in both chemical and kinetic, you lose chemical while kinetic is preserved. That's what usually happens. You can find situations where these are actually not consequence of the other, and maybe you have chemical without kinetic, you have kinetic before chemical, but then the simplified treatment I'm about to give is not valid, and there are studies, there are papers that they do the Rayleigh calculation properly in that case. And if you want to call it freeze out, you can call it freeze out because eventually you have chemical equilibrium, but it's not the freeze out that you solve with this Boltzmann equation. But yeah, of course, that's true. You can have chemical without kinetic. There are models where this happens. Okay. So how do we do this calculation? So let's write finally the form of the Boltzmann equation. So d n chi dt plus 3h n chi. Okay, now let me do the following. First of all, I take out immediately the piece that was bothering me, okay? So this piece in the square bracket out of the integral. And here I define gamma chi, a new function. This gamma chi, the name I use to call this is not the collision operator, it's the collision rate, okay? The operator, as the name suggests, is something that acts on the distribution function of the dark matter. There is no distribution function of dark matter here, so it's not an operator. It's a collision term or a collision rate. It's the number of interactions per unit time and volume. So it has a mass dimension 4, okay? Number of events per unit and time and volume. And the explicit expression of gamma chi is the following. Now I have to be careful the way I write that. I have to write it in a way that makes sense. So I isolate first And then I will explain, of course. So I do first the integral over the dark matter momentum, okay? Then I have f chi equilibrium of P1, f chi equilibrium of P2. Why? I have F1 and F2. Remember, conservation of energy, they are the same. So I'm using what I already proved, okay? F1, F2 at the equilibrium are equal to F chi bar at the equilibrium, just because in the Maxwell-Boltzmann, the energy goes as the argument of the exponent, and then the energy is conserved. Then in the second line, I have, I write this in this form. It's 1 over 4 A1 E2 M square D4 P initial minus P final G1 D3 K1 over 2 pi cube I will change it a bit. Just give me 1 second. So I bring these factors of E here. Okay. So here I had 2 E chi bar. They become 4 E chi bar. And then I didn't touch anything here. Okay. So I wrote this expression in this form because this should remind you what you find in textbooks, okay? In textbooks, it looks very similar to a cross-section. It is not a cross-section. It is m square delta 4, and sorry, there is also a 2 pi to the 4, of course, so this is the conservation of energy. You have phase space where you sum over all the possible final states, okay? And then you have this flux factor, which is not the complete flux factor, is something that is missing what is known as the Mueller velocity, not the relative velocity. So the Mueller velocity is something that you can define that coincides with the relative velocity when the two momenta of the initial states are on the same axis. Otherwise, there is a correction, okay? So, in other words, what I'm doing, I have on the second line, let me point this out here. This is sigma times V M, V Mueller. We will call it V, okay? And it's often referred to the relative velocity, but let's be precise since the first time we mentioned that, okay? So I have this combination here, and this is, of course, a function of the initial states, because in this line, the initial states are fixed. Initial states for the chi bar collision, okay? They are fixed. They have to conserve energy and momentum. And then I sum over all the possible final states. I'm summing because there is also G1 and G2 here. So the first line tells me that I'm taking the sum over the possible initial states, but not just a random sum, a sum with a very specific weight. And the weight is the statistical distribution at the equilibrium, okay? So if you normalize this average that you take, then the gamma chi factor is 1 over n chi equilibrium squared times the thermal average of sigma V, where V and Vm, I will call it V from now on, okay? And the reason why, I'm sorry. this is the right equation, okay? Even dimensionally didn't make sense before, okay? So this is the expression for the collision term, the collision rate, okay? And keep in mind that this one depends on T, and also this one. Because I'm doing a thermal average of the cross-section, of course, it must depend on the temperature, and also the equilibrium number density depends on the temperature, okay? So if you put all the pieces together, you get the Boltzmann equation for WIMPs. Which I'm gonna rewrite in the way you find commonly. Okay, that's the form where you probably see it in textbooks and papers. Okay, and I would like to mention that you know, this derivation is something that is established. If you want to look at a very nice paper where this thermal average is derived and defined and all the Boltzmann distribution is solved and it's all discussed, and this is the paper where I learned this, is by Gondolo and Gelmini, the same Gelmini who was in this room this morning from 1991, okay? So this is a seminal paper on the subject that, first of all, taught me how to do relic density calculations, and also taught everybody how to improve the predictions that were made at the time. Okay, so this is a paper I strongly suggest if you want to look at a good reference explaining this. Okay, so now we have this equation. Please. Yes, yes, I didn't have to if I wanted to. So in the notes, I'm being very systematic. We'll discuss all the cases. Now, I wanted to simplify my life, but you are right. If I do not assume that they are equal, I can still get away with that. But then I get in the Boltzmann equation nchi times nchi bar. Okay, exactly. Yes, yes, I agree. And you know, if they have different distributions, then you have to do twice as much the work you do, because you have to write also an equation for nchi bar, where you have the left-hand side, the nchi bar, dt 3h nchi bar. So the Liouville operator will be the same. But here, then you will have the correction. But you are absolutely right. So in this sense, if you wanted to assume that the equation integral differential became ordinary, that assumption was not needed. That assumption was not needed. It was just you had a system of two coupled equations. But yes, I agree. Yes, I agree. Other questions or comments? Thank you for this one. Okay, so we have 10 minutes left, so I can sketch the solution, because now this is an equation, it's called of the Riccati type. It doesn't have a closed solution, so if you want to do things seriously, you have to solve it numerically, okay? But we can sketch the solution as follows. So the way we sketch the solution is by writing down the equation in dimensionless and comoving variables, okay? So the first thing I do is to write y chi and chi over s, okay? So you can prove that dy chi dt, this time derivative, okay, is equal to what? Is equal to t dt. There is an easy way to compute this derivative. This is just a definition. You multiply a cube on both sides, above and below. So far I did nothing. Then I use entropy conservation. So this goes out of the derivative, okay? 1 over s a cube d dt and chi a cube. And then I do the derivative with the Leibniz rule, and I find something I know very well, which is d and chi dt plus 3h and chi, okay? So I just use entropy conservation to say that this combination is constant, so I take it out of the derivative. Okay, so now I recognize here the left-hand side of the Boltzmann equation. So I can say, okay, you know what? S dy chi dt is equal to dn chi dt plus 3h and chi, but I know what it is, okay? So I have minus sigma v, and then I write this as follows, as s squared y chi minus y chi equilibrium. Why? Because s squared gives me the y inside the parentheses, okay? So I can simplify a power of s. So this is one necessary step. It's not the last one, because also we would like to use the temperature as a variable. So dy chi dt, that's what I would like to use. Eventually x, but for now let's say t. Dy chi dt is equal to dy chi dt dt, okay? And then remember, we computed this yesterday, okay? Was minus, I have to put in the denominator, h times t, okay? And then, of course, I read the other part from above. So the minus becomes a plus. Okay? I'm not happy because I want to use x as a variable, okay? But remember, the mass is constant, so you have d log t plus d log x equal to 0. Because you bring the t here, you take the differential, and you find that they are equal. So you do a change of variable, and you find dy chi d log x is equal to minus, there is an s missing, right? Was that the comment? Yeah, okay, good. So I have and this is the final equation, okay? Now, of course, I have the entropy density, which is a function of x. I have Hubble, which is a function of x. And this dependence on x is something I know, because I know how to express Hubble as a function of t, and I know how to express t as a function of x, by the definition of x, okay? Sigma v is also a function of x in general. We have discussed the S-wave expansion yesterday, the S-wave approximation, but if you want to be general, you can keep all the dependence. And since we have a few minutes, let's discuss what happens. What happens after freeze out, okay? What happens after freeze out? But before I do that, let's simplify the equation a bit more. And a bit more I do this. I say sigma v equals sigma 0. This is the approximation we made yesterday, okay? So this is called S-wave approximation. Then you can write the equation as dy chi dx is equal to minus lambda x square y chi square minus y chi equilibrium square. What is lambda? Lambda is sigma 0 S for x equal 1 divided by Hubble for x equal 1. Okay? This is just a definition. So this is an equivalent form. Now, if I want to discuss this solution for x larger than xf, remember, as long as x is below xf, we are in equilibrium. There is not much to discuss. We can still build an approximate solution, but we're very close from equilibrium. The interesting action is for x greater than xf. That's when I go away from equilibrium. So in this case, I can simplify. And again, if I want to do things properly, I do the numerical job, okay? But I can simplify this equation by this expression. Why? Yes? Why? Oh, remember, sorry, I was fast. This is log x, this is x. X squared, yes, because Hubble goes like s to the minus 2, and s like x to the minus 3. So you have 1 plus 1, 2. Yeah, but this log, the reason is this log. Okay. So what did I do here? I just neglected this. But it makes sense. Because after freeze out, the y chi starts to decouple from equilibrium. And the equilibrium is dropping exponentially. So this is becoming more and more valid. And this is an equation that I can integrate very easily just by separation of variables. I bring the y chi here, I bring the x here, it's straightforward to integrate, okay? And so let's do that to conclude the lecture. So if I take that equation and I say, okay, let's try to solve that. Okay, I have this on this side. Right? Yes, it's correct, right? Yeah. So, okay. Can be solved. Okay, I will not do the solution, but it's straightforward. And, you know, we do the matching, of course, of this solution. By matching, I mean that we say that y chi at xf, so when you solve this equation as initial condition, you better ensure this, so you get the continuous function. Okay, but if you do this, then going back to the plot we started from today, so let me put the plot here so we conclude the discussion. We are perfectly in time. If now you go back to this plot and you have y chi as a function of x, this is the equilibrium one, and this is the freeze out point, then the behavior after freeze out, I'm exaggerating here, this is the instantaneous approximation, okay? The behavior after freeze out and the additional depletion with respect to the instantaneous approximation after freeze out, it's something that is described by this differential equation. And you know, I will give in the notes the full solution, but this is easy to solve. You also impose this boundary condition, and you are done. Okay, so tomorrow we will go back to the initial division between freeze out and freeze in. In this case, we assume kinetic equilibrium. And thanks to kinetic equilibrium, we were able to find a differential equation we can work with. Tomorrow, we go in the opposite case when f chi over f chi is basically negligible. And then we will discuss what happens. And so I will stop here for today.
Actually, I want to verify. So for S squared, sigma is sigma naught. It's not sigma naught be thermal.
Well, sigma naught is just a symbol I'm using. So I'm calling it the S-wave approximation. No, no. So V is dimensionless in natural units. So that's why sigma V has the same dimension. But sigma naught is just a constant. I'm just using that symbol to denote a constant. A question? Yeah.
Is there any case where you need to use density matrix rather than the phase space distribution, like for the positive statistical description?
Not in this context, not in the context of these kind of candidates that thermalize in this way. Not to my knowledge. I don't know.
Dark matter, there's now kind of a set of recent works that is showing that even there where you could in principle have that, in practice it seems like we're never really, these particles are independent, thermal, you don't get, you need coherent stuff in order for the...
Exactly, but this is below the EV, right? So yeah, so
it seems like you probably done that.
yeah, so the organizers did a great job for this group because they divided the 2 weeks into particle and wave dark matter. So yeah, whatever I've been telling you today is about particle dark matter. So I have masses above the EV. You remember in the lecture by Graciela yesterday, she had this distinction between these two regimes. I am on the right of that plot. So in this case, no, the answer is no. This is enough.
Anything else? We can reconvene for the...
Coffee break
What, we go for coffee and then reconvene
for the student presentation.